Welcome to this explainer. Today, we're going to step out of the ordinary world and head straight down a truly fascinating mathematical rabbit hole. We are exploring group theory. Now, this isn't just a bunch of numbers on a page. It's literally the fundamental language of structure itself. I'm super excited to be your guide, so let's just jump right in.
Here's our map to this mathematical wonderland. We'll cover 1. What is a group? 2. The 4 rules. 3. Clockwork math. 4. Looking glass geometry. 5. The Rubik's Cube. And finally, 6. The language of structure.
Section 1. What is a group? Stepping into the mathematical wonderland. Okay, let's dive into this. If I were to ask you what a group is in everyday life, you'd probably point to a group of people or maybe a cluster of dots. We usually just mean a collection of things. But in mathematics, it's so much more profound than that. A mathematical group isn't just some passive collection. It's a completely stable, reliable structure of things and actions. The things and the actions actually have to work together. Stepping into this wonderland means wrapping our heads around the idea that a set alone is really just a box of objects. A group only actually comes to life when we add an operation. Basically, it needs a reliable rule for how those objects combine, interact, and transform. Section 2. The 4 group rules. Basically, the laws of physics in Wonderland.
To navigate this new space, we absolutely have to understand the 4 foundational rules that our set and our operation must follow. Rule number 1 is closure. This just means if you take any 2 elements, let's call them A and B, that live in our set and combine them using our operation, the result is always going to be another element that's also in the set. Whatever actions we take, we're completely bound to this set. We never leave it.
Rule number 2 is the identity. In every single group, there has to be a very special element that changes absolutely nothing. Think about it. No matter what you combine this identity element with, the original element stays exactly as it is. It's this reassuring, totally stable action of keeping things completely untouched. Rule number 3 is the inverse. And honestly, this is probably the most comforting rule of this entire mathematical universe. Every single element has an undoing element, meaning for every action you take, there is a specific, almost magical reverse action that brings you right back to the identity, right back to square one. Every action can be perfectly undone. The final rule is associativity. This simply means that when we combine multiple elements in a row, the way we group our actions won't change our final destination. Grouping just doesn't change the result. So, if a structure has these 4 properties, closure, identity, inverse, and associativity, boom, it is officially a group. Section 3, Clockwork Math. Time acting strangely. Now that we've got the rules down, let's make our first stop in a place where numbers literally loop around in circles. But before we look at the actual numbers, let's establish a bit of a rhythm. Every time we look at a new example today, we're going to anchor ourselves by asking 4 grounding questions. What is the set? What is the operation? What is the identity? And what is the inverse? Now, what's really interesting about this slide is how time acts so strangely here. We're looking at C7, where numbers live on a 7 o'clock. Our set is just the numbers 0 through 6. Our operation, addition modulo 7. So if you're at 5 and you add 4, you don't get 9. You move 4 spaces around the clock and land right at 2. So in this world, 5 plus 4 equals 2. The identity is 0, because adding 0 obviously changes nothing. And the inverse of 5? Well, it's 2, because 5 plus 2 brings you all the way back around to 0. Section 4, Looking glass geometry. Flipping things in a mirror. Let's leave numbers behind for a second and step into the looking glass world of shapes and reflections. Take an equilateral triangle. Here, our set is entirely different. We aren't looking at numbers, we're looking at symmetries. There are exactly 6 physical actions that leave this triangle looking exactly the same as when it started. Things like rotations, turning the triangle, and reflections, like flipping it across an axis in a mirror. And our operation here is called composition, which is just a fancy way of saying doing one physical action and then doing another. Let's move to and see how this builds into our group rules. Say, step 1, we rotate the triangle 120 degrees. Then, step 2, we reflect it across its axis. What's the result? Well, the result of composing these 2 distinct actions is always going to be another single symmetry that already exists in our original set of 6. It's a perfect physical demonstration of closure. Section 5, the Rubik's Cube puzzle. The ultimate puzzle box. For our third stop, we're looking at the ultimate puzzle box. It's something you've probably held in your own hands, completely unaware that you are playing with a tangible piece of abstract algebra. Rubik's Cube moves form a group, because moves can be composed and undone. Let's bring back those central literacy questions. The set, every single possible position of the cube. The operation, composing sequences of face turns. The identity, doing absolutely nothing to the cube. And the inverse, simply turning a face back the exact opposite way you just turned it. So the crucial point is this really deep yet totally accessible observation about the cube. Order absolutely matters. Doing a right turn and then a top turn gives you a vastly different pattern than doing a top turn and then a right turn. In math terms, we say this specific group does not commute. The sequence of your actions completely changes the outcome, showing just how beautifully complex these structures can get.
Section 6. The language of structure. The awakening.
We've journeyed through looping clocks, rotating triangles, and complex puzzle cubes. Now, let's slowly pull back to reality. Group theory connects arithmetic, geometry, puzzles, coding, chemistry, physics, and even art. The goal of this explainer isn't to make you memorize algebra. The real goal is to open your eyes to this profound universal language for studying actions that preserve, transform, combine, and undo structures everywhere in the universe.
To summarize everything we've talked about today, it really just comes down to this. A group is a world where actions can be combined and undone. That's it. It cuts right through all the complex equations and reveals the simple, almost magical heartbeat of group theory. As we wrap up our journey today, I want to leave you with one final provocative thought. Now that you know the rules, closure, identity, inverse, and associativity, look at the patterns around you. Where else in your everyday life do you see these stable structures of actions? Where do you see things interacting that can be perfectly combined and magically undone? Keep your curiosity alive, because the language of structure is literally everywhere. Thanks so much for exploring this with me.